let us discuss chemical potential more in detail. For a pure substance, one can write del mu as minus S dt plus V dP. Now, these are in molar properties. Okay. Now, the question is that how do you connect chemical potential to more physically measurable quantities, right? And that is basically the challenge. Though Gibbs was the one who basically obtained thermodynamic solution to the phase equilibria by introducing chemical potential, but this is an abstract concept, right? So, what we are trying to do is to understand the issues with the chemical potential calculation. So, let us try to integrate this. If you integrate this, okay, I can write mu as Tp. This would be equal to mu at some reference temperature and pressure, because you have integrated, minus Tr to T S dt plus Pr to Pv dP. Okay. Now, R here is an arbitrary reference state. So, in principle, you can calculate this using thermodynamic expressions and volumetric data. We have shown this, that we should be able to calculate the changes in entropy if you can make use of Maxwell relations and so forth. So, in principle, you should be able to calculate thermodynamic expressions and volumetric data, but there is a issue of reference temperatures or reference conditions. More importantly, this we do not know. Okay, this is unknown, okay, and thus due to the need of an arbitrary reference or standard state, the successful application of this expression depends on the judicial choice of the reference, okay, and that makes it difficult for practical applications. Okay, it is not a problem if you want to find out changes in the chemical potential, because this will cancel out, okay, but for getting absolute, so that is not feasible with this kind of expressions. Okay. So, in order to express this chemical potential in more reasonable expressions, first Lewis considered the case of ideal gas. Okay. For the ideal gas, and if you consider the expression of del mu by del P for a pure system, this is nothing but molar volume, that is what we have derived earlier, and for an ideal gas this is RT by P. Okay. So, if you integrate this, okay, what you get? Mu minus mu 0, this is RT ln of P by P 0. So, you can relate chemical potential difference to the changes in the pressure in the logarithmic value, okay. But there is an issue. Okay. So, note here that what is mu 0? Mu 0 and P 0 are at this particular temperature. Okay. So, all the substances approaches an ideal gas behavior at very low pressure, okay, or very high temperature. So, if you consider a very low pressure, okay, then mu is, if pressure is tending 0, what is the value of mu? Mu is going to be minus infinity. But this is where all the substances approaches ideal gas. So, which essentially means we have an issue here, that this is a very unusual condition. So, this kind of situation is highly undesirable, right. The reason is because ideal gas is approached at low pressure for all substances. Okay. And this expression of the chemical potential is a key to the thermodynamic analysis. Okay. So, how do you avoid this logarithmic divergence of chemical potential at low pressure? So, Lewis introduced fugacity in order to avoid such a situation. So, the definition of the fugacity is ln f by f 0, this is mu of T p minus the reference mu T at the pressure P 0. Okay. This is the reference pressure. Temperature is kept same. Usually this is taken as 1 bar. Okay. Note this is a ratio. So, this can be any arbitrary unit. Okay. But in practice people take this to be 1 bar. Okay. But fugacity is certainly not a pressure. Okay. It relates to the chemical potential. So, it is not an equivalent of pressure. The other thing which one should note is that since chemical potential depends on two intensive variable T and P, the fugacity also depends on T and P. Okay. Now, this mu 0 and F 0 are arbitrary again. Okay. But are they independent? The answer is no. Once you fix mu 0, the corresponding F 0 is fixed. Okay. Okay. The other thing is that unlike the chemical potential, F does not diverge. So, when you consider F 0 is equal to P 0, let us say is 1. Okay. And if you compare this expression with the earlier expression mu 0, this expression, okay, when you consider F 0 is equal to P 0 is equal to 1 and you plug in here, you can show that because that other expression is for ideal gas. So, this is for ideal gas, right. Okay. For an ideal gas, F 0 is equal to P 0 is equal to 1 as a reference would mean that Fig by okay. So, this you can derive because mu minus mu 0 is basically nothing but RT ln P by P 0 okay, for an ideal gas, and since F 0 is equal to P 0 equal to 1, you should be able to find out you should be able to get this expression. Okay. Now, the other thing is sometimes we also defined terms like an auxiliary quantity F by P, okay, and for gas F by P or phi tends to 1 as P tends to 1. So, when you choose of course F 0 P 0 is equal to 1. Okay. So, let me further continue with this fugacity expression. Let me go back to the definition of or the relation of the partial derivative of mu with respect to P, which is related to V. Okay. Now, with this definition is irrespective of whether the fluid is ideal or not. Okay. But the relation of the chemical potential to pressure in this form depends on whether the fluid is ideal gas or in other words this holds for ideal gas. So, we again go back to this expression del mu by del P at constant V, okay, and this mu we know now with respect to fugacity. So, we have this relation mu minus mu 0 is equal to RT ln F for a constant temperature. Okay, this can be now written as RT del N F by del P at constant T, or in other word mu 2 minus mu 1 is RT ln F2 by F1. Okay, this is nothing but because you are integrating with respect to pressure. So, this is nothing but dP P1 to P2. Okay. So, now I can rewrite this expression. I can also write it like ln F2 is equal to ln F1 plus P1 P2 V by RT dP. Okay. Right. Now, this is basically a generic expression. Okay. And what we have done is we have not made any assumption here, if you look at it very carefully. Now, for the case of liquid and solid, we can try to assume that it is incompressible, that means molar volume is almost constant, we can take it out. In that case, I can write F2 is equal to F1 exponential, and this is nothing but Poynting correction. Okay, so in other words, I should be able to calculate the fugacity, at least the ratio of the fugacity from the known value of the molar property, okay, and the changes in the pressure for a given temperature, okay, for any system. So, let me just do a very simple example why we can simply consider in this way and not necessarily integrate it. So, there are two equations, right. One is the case where we have this, where it talks about just integration of V by RT dP, and this another one which approximate it, but this is for solid and liquid, assuming this is more or less constant. Okay. So, this is a problem which we can look at. This is an example. So, the question is, we have to calculate the change in fugacity of liquid water at 300 Kelvin when pressure is increased from 0.1 megapascal to 100 megapascal. Okay, so, basically 1000 times increase in the pressure, and the data for this can be obtained from NIST Web of Science or NIST web book, okay, which is available without any special privileges. You can just type it and you can get this information. What are the information you need? Temperature is already given. What you need is basically nothing but molar volume of the water, liquid water, as a function of pressure, because we are going to make use of the expression. Okay. So, as I said, there are two expressions which we have considered. This is the one without any approximation, right. So, we can use trapezoidal rules for numerical integration. Okay. So, let us assume that you have pressure given in megapascal like 0.1, 10, 20, 30. Okay. And the molar volume is given as 1.81 into 10 to the power minus 5, 1.80 into 10 to the power minus 5, 0.79, okay. So, these are all the values directly from the NIST web book. Okay. Okay. Now, so what is the value of this integral? Okay. So, we can consider, since it is being asked the change in fugacity, okay, not the value of the fugacity. So, we can consider this as a reference 0.1. Okay. So, if we consider this as a reference, then we should be able to find out the fugacity ratio at 10 megapascal with reference to the fugacity at 0.1 megapascal. So, this is the values of the integral, and this would be your f by or f2 by f1. Okay. So, if we just if we are just considering this, then of course, this is going to be 1. Okay, this is going to be 1.07, 1.15 and so forth up to 2.04. So, this is the value 2.04 which comes at 100 megapascal. Okay. So, in other words, getting from 0.1 to 100 megapascal, the ratio of change in the fugacity is 2.04. Okay. Now, if you use the second expression, which is a Poynting expression, okay, how are you going to do that? You can consider the molar volume at 0.1 megapascal to be constant. So, F2 by F1 is exponential V delta P by RT, right. So, this is exponential. What is V? V is whatever we have considered here. This is the molar volume at 0.1 megapascal. So, this is 1.81 into 10 to the power minus 5 meter cube per mole multiplied by the change in the pressure, which is 100 minus 0.1 megapascal, which is 99.9 into 10 to the power 6 Pascal, okay, divided by gas constant, which is 8.314 joules per mole Kelvin, multiplied by the temperature. The temperature was 300 Kelvin. Okay, so we just put 300 here. Okay, now this turns out to be 2.06. Okay, so on one hand you have done a very rigorous trapezoidal based calculations, which you can of course do using Excel without writing codes also. The value turns out to be 2.04, and on the other hand, if you use simply the Poynting expression, the value turns out to be almost close enough. Okay, and the reason why it is negligible, because water in this condition turns out to be incompressible. Okay, so I will stop here, and now in the next lecture I am going to continue the general discussion on the fugacity and its relation to the phase equilibrium.